synchronous counter. So last class we already discussed, okay, 2, 5, 3, 4, 1, 7. Still I am repeating again, okay. So in synchronous counter, so whatever clock we are giving, that is common compared to asynchronous counter. Synchronous counter clock is common. Now I need to be built, and one more thing I told, random counting can be possible in synchronous counter. Not be possible. Third thing is anything skipping. See here 2. So next directly I am counting 5. In between whatever numbers are there, I skip those things. Anything skipping can be possible in the synchronous counter. That will not possible in the asynchronous counter. So now I need to count these things. First I need to count to 2, 5, 3, 4, 1, 7. So next again it will be 2, 5, 3, 4, 1, 7. Like that I need to count. So now first what we need to do when we are building this synchronous counter, first I need to see when I am counting in these entities, which one is maximum number. Which one is maximum number? In this, which one is maximum number? 7. 7 is a maximum number. To represent 7 in the binary, how many bits required? 3 bits required, right? 1, 1, 1. Minimum 3 bits are required to represent this 1, 1, 1. So now, so 3 bits means 3 outputs. Present state, next state. So this Q2, Q1, Q0. 3 bits. Okay? 3 bits. So now next state Q2, Q1, Q0. 3 bits. Clear? So now present, what is the present value? First you are starting with 2. 0, 1, 0. This is a 2. This is a 2. So now present state is 2. Next state is next state is 5. 1, 0, 1. So now from here to here we went. Now present state is 5. 1, 0, 1. Next state is 3. 0, 1, 1. So now present state is 3. 0, 1, 1. Next state is 4. 1, 0, 0. So now present state is 4. 1, 0, 0. Next state is 1, 0, 0, 1. Now present state is 1. Next state is 7. 1, 1, 1. Now present state is next state is 2. 0, 1, 0. So now this I want to implement in JK. I can implement in the JK. I can implement in the D. So any flip-flop I can take and I can implement. To implement that, we need to know the excitation table of that flip-flop. That's it. So D, it is simple. So whatever Q2 is there, Q1 is there, Q0 is there, that is D2, D1, D0. Very easily we can implement with D. Okay. So when someone will ask in the interviews, go with the D flip-flop. But now, so you need to know all the possible cases, right? So that's why I'm going with JK. Clear? So we'll go with JK. J2, K2, J1, K1, J0, K0. These are the things. So now, so I need to know the excitation table, right? So Q of T plus 1. Present state, this is a next state. This is 0, 0, 0, 1, 1, 0, 1, 1. 4 cases will be there. J and K. So now this excitation table 0, 0, 0, 0. 1 don't care. 0, 0. No. 0, 0. 0 don't care. 0 don't care. Clear? 0, 0. 0 don't care. 0, 1. 1 don't care. 1, 0. Don't care. 1. 1, 1. Don't care. 0. Let's confirm again. 1 1 don't care 0, 1 0 don't care 1, 0 1, 1 don't care. Yes. So now, so based on these values, you need to, you are getting these things, right? So now simply you need to check, okay? So when you are J to K2, you are implementing, you need to check Q2, Q2, present state Q2, next state Q2. So this one is 0, this one is 1. 0, 1 means 1 don't care, 1 don't care. 1 0, 1 0, 1 0 don't care, 1. 0 1, 0 1, 1 don't care. 1 0, 1 0 don't care, 1. 0 1, 1 don't care. 1 0 don't care, 1. Clear? And one more thing I forgot it. So here, if you observe, okay, 3 bits maximum, how many we will count? We will count 7. Okay, 0 to 7, total 8 bits we can count. But here, how many bits we are counting? 1, 2, 3, 4, 5, 6. 2 bits are missing. Which 0 and 6 bits are missing. These also don't care. When you are implementing KMap, these also you need to consider. Okay, 0, 6, these are the don't care. So now J1, K1 you need to be checked. So J1 is Q1. This is Q1 you need to check. 1 0 don't care, 1. So 0 is 1, 0 1, 1 don't care, 1 0. This one screen becomes blank and coming. Suraj is there? Suraj is there? Event. Online guys, screen is visible, right? Can you please chart and confirm?
Yes, sir.
So 1 0, 1 0 don't care, 1. 0 0, 0 0, 0 don't care. So 0 1, 0 1, 1 don't care. So 1 1 don't care, 0 don't care, 0. So now next 0 1, 0 1, 1 don't care, right? 1 don't care. 1 1, don't care 0. 1 0, don't care 1. 0 1, 1 don't care. 1 1, don't care 0. 1 0, don't care 1. Clear? This is the table. So we need to complete this table. So to complete this one, so you need to know this excitation table, then only you can easily implement this one. Clear? So now for each and every J2, K2, J1, K1, J0, K0, for each and every, okay, so output, you need to be implement the K-map. Just 1 minute. Yeah. So each and every J2, K2, J1, K1, J0, K0, we need to implement the K-map. Clear? So now, so we'll go with the J2. So how many variables of K-map? 3 inputs are there, right? 3 variable of K-map I need to be implement. So 3 variable of K-map. Q2, Q1, Q0. So 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. This is a 0. This is 1, 2, 3, 4, 5, 6, 7. Clear? So this is the thing. So now this is a 2. This is 5. This is 3, 4, 1, 7. Clear? So now you need to check J2 when it is 1. J2 is 1 at 2, 3 and 1. 2, 3, 1. 1, 2, 3. It is 1. 1, 2, 3. It is 1. So when it is don't care, so it is don't care at 5. 5, 4, 7. 5, 4, 7. So one more thing I already told. Okay, these two also need to be considered. Don't care when you are implementing K-map. 0 and 6. 0. This is don't care and 6 also don't care. So when you are implementing, so you need to check first maximum 8 mapping. Next 4 mapping. Here all are present. I can map all 8. So if I will map these all 8, what I will get? I will get 1. So now J2 equal to 1. So I need to give, when implementing the circuit, I need to give J2 equal to 1. So next we'll implement K2. Q2, Q1, Q0. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So now this is K2. So K2 when it is high at 5, 4, 7. 5, 4, 7. It is high. So 5, 4, 7 it is high. So when it is don't care, is don't care at 2, 3, 1. 2, 3, 1. 2, 3, 1. And 0 and this one also 6 don't care. So these all we can map. If all we map, what we will get? K2 equal to 1. J2 equal to 1, K2 equal to 1. So now next we need to go with J1. Q2, Q1, Q0. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So now next, in this, okay, J1, when it is high at 5 and 1. 5 and 1. In this condition, it is high and it is high at 1. In this condition, it is high. So remaining when it is don't care, it is at 2, 3 and 7. 2, 3, 7. So 2 it is don't care, 3 it is don't care, and 7 it is don't care. And one more thing, 0 and 6 also don't care. So now how many maximum I can map here? I can't map 8, right? Because here 8, all 8 are present, I mapped. Here I can't map 8. So next what I need to check? I need to check for 4. So in the 4, these 2 also covered, I need to check. So these 2 also covered, right? If I will 4, I will map this 4, these 2 also covered. But if I will map this 4, only 1 will be covered. So I need to check for all the ones should be covered. Okay. So here in this mapping, all the ones should be covered. So don't care, sir. You can consider or you can't consider. Depends on the mapping. Okay. So now I map this 4. What is the output I will get? J1. What is the common? Q2 is not common. Q2 is 0, 1. It is changing when it is mapping 4. But in these two, what is the common? Q1 is 0. Here it is 1. But Q0 it is 1 here, it is 1 here. Means Q0 is maintaining same, right? In this both condition. So now J1 equal to Q1. Q0, sorry. Q0 is same, it is 1, right? So that's why Q0. If this one is 0, then it will be Q0 bar. Clear? So this one is a J1. So now next K1. We need to take Q2, Q1, Q0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So now here K1. So if you observe when it is high at 2, at 3, and 2 and 3, only 2. 2 and this it is high, here it is high. So this one 0 is don't care, 6 is don't care, no doubt in that. Okay, so remaining what other things don't care are there? 5, 4, 1. 5, 4, 1 are don't care. So this is a 5, 4, 1. Where is the 1? Wait, I think previously something I did wrong. When it is high at 2 and 2 and J1, K1, 2 and 3, right? Okay. 2 means this one. This one is don't care. 2 means this one. Okay. So now, so this is the don't care. So 7 condition it is 7, it is 0. So it is, we can't map. 8 mapping is not possible. So then I need to check for 4 mapping. So in the 4 mapping also, all 1 should be covered like that. I need to map. So which one is better to map? This one, right? Yes or no? Yes. So we can map this one and this one also, but this one will be left. That's the reason I'm mapping these all the things. So then what is the common in this all? These two variables are changing in this all, but this Q2 is 0 in this all the common. Getting? So this Q2 I need to be take, it is 0. That's why it will be Q2 bar. If it is 0, we'll get the bar. If it is not a 0, we'll get directly Q2. This is the K1. Next, J0. Q2, Q1, Q0. So now J0, when it is high at 2 and it is high at 4. 4. 2 and 4 it is high. 2 and 4. 2 is this one. 2 and 4 it is high. So this one and this one is don't care, we already knows. Clear? So now, so remaining other don't cares are at 5, 3, 1, 7. 5, 3, 1, 7. 5. This one is 5. This one is 3, 1, 7. Yes or no? 7 is this one. Yes or no? So all are mapping. So what we will get? J0 equal to 1. J0 equal to 1. So any zeros are there? Simple. If any zeros are not there, then it will be simply 1. Okay. So next K0, final one. So here, so at 3 it is high, at 7 it is high. 3 it is high, 7 it is high. So where it is don't care, at 2 it is don't care, and 2 it is don't care, and 4 it is don't care. 2 and 4. This is 4 don't care, 2 this is 2 don't care, and this 1 also don't care, and 6 also don't care. Clear? So how many maximum mapping I can do? 4, right? 2 are empty, right? 4 I can map. This 4 if I will map, Q2 is not common, 0, 1 it is changing in this 4. But if you are observe here, which one is common? Q1 is here 1, here 1. Means Q1 is common. So now K0 equal to Q1. Clear? Q1. So now 3 bits. So 3 bits Q2, Q1, Q0. So you need to be take 3 flip-flops. 3 JK flip-flops you need to be take. So clock is common. CLK. All are positive trigger. J0, K0. This is Q0. Q0 bar. J1, K1, Q1, Q1 bar. J2, K2, Q2, Q2 bar. Clear? So now we'll see the circuit. So J2 equal to 1, K2 equal to 1. So what I need to do? J2, K2. This one, 1. This one is 1. Clear? 1 means you need to connect VDD. Simply, if I want to say, you can connect to VDD. Clear? So now, next is J1 is Q0, K1 is Q2 bar. J1 is Q0 directly. We need to connect this. Okay. J1 is Q0, K1 is Q2 bar. This whatever Q2 bar is there, this you need to bring. This you need to connect here. Clear? Q2 bar. So next J0 is 1, K0 is Q1. J0 is 1, K0 is Q1, this one, whatever this output is there, right? This output, we need to connect to this. So this is the output we'll take from here. This is the output and this is the output we'll take. This is MSB, this is LSB. So these are the three outputs we'll take. So this is the whatever we counted, right? This one. So this 2, 5, 3, 4, 1, 7, it will count. This circuit will count 2, 5, 1, 7. So it will count, those things will count by this circuit. Clear? So what are the steps we followed? We followed first, okay. So which one is present state, which one is first bit? Check, okay, which one is maximum number? How many bits we can represent, okay, with max 3 bits. So then, so 3 bits present state, 3 bits next state, okay. So present state means first 2, next state means 5. Now present state becomes 5, next state becomes 3. Now present state is 3, next state is 4. Like that we done first this. So based on the excitation table, we identify J2, K2, J1, K1, J0, K0. So after that, each and every output, so we run the K map. So then we solve the equations. Based on these equations, we implemented the circuit. Simple. Clear? Any questions, any doubts here? Online guys, any questions, any doubts? This one. This is 2, right? 0, 1, 0. This is 1, this is 2. Which chart?
0, 1, 0, 1, 0, 1, 0.
This is binary numbers. 0 you will represent in the binary 0, 0, 0. 1 you will represent 0, 0, 1. So behind this, what it will be means 2 power. So generally how it will represent means, wait, I will tell you. Hmm? Wait. So this one is 2 is 0, 1, 0. 3 is 0, 1, 1. Generally, this one is 1, this one is 2, this one is 4, next 8. Like this, it will be there. Okay. This one indicate, okay, 1. This one indicate 2. This one indicate 4. So when it is becomes 1, right? 1 means here it is indicating 1 means 1. Here 1 means it is 2. Here 2 plus 1, 2 plus 1, 3. Getting? So now same way 4 means 1, 0, 0. 4 means directly I can take only 1, right? 5 means 4, 0, 1. 4 plus 1, 5. 6 means 1, 1, 0. 4 plus 2, 6. 7 means 1, 1, 1. All are 1. 4 plus 2 plus 1, 7. When go to the 8, so you need to add one more bit. 1, 0, 0, 0. This is the 8th. Getting? So like that. Getting? So this is the thing. BCD. So this is the circuit. Clear? So now understand this one, right? So keep a heading. Next topic, shift registers. Shift registers. Shift registers. First, the basic question in the interview they will ask is, what is the difference between latch, flip-flop, register? Because these are the basic elements which we will use in the digital electronics. Yes or no? All three are memory elements, no doubt. All will store the data, no doubt. Okay. So latch will store single bit data. Flip-flop will store single bit data. Register will store single bit or more than one bit. What is the difference between latch? Latch is a level triggered. Flip-flop is a edge triggered. So what about the register? What about the register? Register also edge triggered. Register is nothing but, okay, register is equal to flip-flop or combination of flip-flop. We'll call the register. Getting? So combination of flip-flop also we can call register. One flip-flop also we can call register. Getting? Clear? But latch we are not calling register. Only flip-flop we will call register. Clear? So this is the thing. Shift registers I am saying. Shift registers are, for suppose this is a block box. This is a block box if you consider. This is the circuit we need to implement it. That circuit block box if you consider. If I am giving serial input, if I am taking serial output. So this is one type of shift register. Serial input I am giving, serial output I am taking. Serial input I am giving, but parallel output I am taking. This is one type of shift register. Okay. Serial input I am giving, parallel output I am taking. One more type is parallel input I am giving, parallel output I am taking. Parallel input I am giving, serial output I am taking. Clear? First type is serial in, serial out. Second one is serial in, parallel out. Third one is parallel in, parallel out. Fourth one is parallel in, serial out. Clear? These are the four types of shift registers will be there. Shift registers will be there. Four types of shift registers. Clear? Note down this one. Clear? Clear, right? See, this is direct and this one direct. Clear? So now we'll try to implement this serial in, serial out. Keep a heading serial in, serial out. Serial in, serial out, shift register. So serial in, serial out, 4-bit serial in, serial out, shift register I'm saying. So you need to remember in the shift registers, n bit, n flip-flops are required. N bit, n flip-flops are required. This is the first rule, note down. N bits, n bits, n flip-flops are required. N flip-flops are required. So now here 4 bits means how many flops are required? 4 flops are required, no doubt in that. So 4 flops are required. We'll draw the 4 flops. Which flops I need to take? Which type of flop I need to take? Shift register I'm saying. Shift register will be used to only shifting the data. Okay, data should not change. Which flop I need to take? D flip-flop I need to take. D flip-flop will not change any data. Okay, whatever the data input is there, same data it will give as a output. Okay, so this one is D0, Q0. Okay, clock is CLK clock is common. This is D1, Q1. This is directly connected. D2, Q2. This is also directly connected. D3, Q3. This is serial out, whatever this one. This one is serial in. Getting? So now this is the thing. Serial input we are giving here. Serial output we are getting there. Clear? So these are the four D flip-flops we are using. All are positive trigger. All are positive triggered. Clear? Clear? So now we'll see. We need to take CLK, SI, so Q0, Q1, Q2, Q3. When I am not giving any inputs, clock is 0. Okay, SI I am not giving anything. Okay, that is also 0, right? So these all are considered 0. Starting, these all are 0. These all are 0. So now I need to shift the data 1010. For example, I need to shift this 1010 data to S into S out, means serial into serial out. 1010 I need to shift. So first what happened when clock pulse 1 positive edge trigger will comes. Okay, so positive edge trigger first clock pulse. Okay, so this 0 data it will take. 0 data this SI will take and it will dump into the Q0. Getting? Q0 means this one is so data I will represent in the red color. So 0 data it will dump in the Q0. Remaining all are same state, right? Remaining all are previous, whatever previous data is there, that data only it will be there. Yes or no? Yes or no? So now next clock pulse, second clock pulse. Second clock pulse, what it will take? It will take 1. It will take 1. So now this one is 1. This one is 1 will be stored in Q0. So now whatever Q0 data will be shifted to Q1. Yes or no? Next. This one is 0. So these both are remaining same. These both are remaining same 0, 0. So next clock 3, third clock pulse. When third clock pulse will come, so okay, one more 0 it will take. Data, one more 0 it will take. This one is one more 0. So this 0 will be stored in Q0. So this one will be stored in Q1. 1 will be stored in Q1. This 0 will be stored in Q2. So then we'll have this one is 0. Clear? These are the up to 3 clock pulses. So next, again CLK, SI, Q0, Q1, Q2, Q3. Yeah. So now fourth clock pulse. Fourth clock pulse, what it will take? It will take 1, right? Input is 1. Input is 1. So when input is 1, Q0 becomes 1. Q0 is 1. So now this 0 will shifted to here, right? Q1 is 0. Q1 is 0 and Q1 is 0. Q2 is 1. Q3 is 0. Q1 is 1. Q2 is 1. Q3 is 0. So this is the first output. First output we are getting. Means, so Q3 means Q3 connected to S4 is S out, right? So first output we are getting here at fourth clock pulse. Fourth clock pulse. So next, so when fifth clock pulse, is there any data we are giving here after this? No, right? 4 bits we given. After that we are giving any data? No. Fifth clock pulse SI is 0, means this one is 0. If any signal is not there, then it will consider as a 0. So this is not a data. Whatever yellow I am representing, those are not a data. Signal is not there. That's it. Okay. So now this one is become 0. So now what happens? Now what happened? This one is shifted to here. This one is shifted to here. This one is shifted to 1. This is the second output. So next, At clock pulse 6, again 0. We are not giving any signal. This one is 0. This one is shifted to here. This one is 0. So next data will be shifted. So this one will be shifted to here. This is 1. This one is shifted to here. This is a third output. So next 7. This is 0, 0. This 0 will shifted to here. This 0 will be shifted to here. So then this one will be shifted to here. This is a fourth output. Clear? Fourth output. So now to shift these 4 bits, how many clock pulses are required? 7 clock pulses are required to shift this 4-bit in, serial out shift registers, 4-bit shift registers. So 7 clock pulses are required. So now in the interview they will ask, okay, or in the MCQ questions, okay, they will ask that 8-bit shift registers. I want to shift 8 bits. How many clock pulses are required for serial in, serial out? No, not 7. Now you need to know the formula.
16.
16. No, 16, we'll see. So the formula for this, okay, number of clock pulses required. Okay, formula for this, number of clock pulses. Pulse required equal to n bits. Okay, so n bits are there. 2n minus 1. This is the formula. 2n minus 1. This is the formula. So number of clock pulses required equal to 2n minus 1. N means here n equal to number of bits. Number of bits. If I am saying, okay, so I have 20 bits. I need to be shifted 20 bits. So how many clock pulses are required means 2 into 20 minus 1. So means 39 bits, 39 clock pulses are required. Getting? So like this they will ask. If you know this formula, then only you can answer that one. Getting? So to know this formula, just I explain this all thing. Clear? So this is the thing. Any questions, any doubts here? Someone chart right here. Clear? This is the thing. 2n minus 1. This is the formula. You need to know. For serial in, serial out. Only for serial in, serial out. So next what is the type? Serial in, parallel out. So now serial in, parallel out. Okay, 4-bit serial in, parallel out I am saying. So 4-bit.
उसमें बीट तो 4 थे ना, वो 20 कहाँ से आए?
No, I'm saying, okay, so this is the formula 2n minus 1. 4 bits are there. 2 into 4 minus 1, 7. 7 clock pulses, which we proved. Okay. So now if in the interview, okay, they ask, okay, so my bits are 20, my bits are 30, my bits are 40. So then how many clock pulses are required? So then you need to be apply this formula and you need to say that these many clock pulses are required. Clear? That is the thing. So now serial in, parallel out. So you need to be give input serially, you need to take output parallelly. So 4 bits, 4 flops you need to be take. All are D flops only. So clock, commonly we'll give the clock. So then this is D0, D1, D2, D3, Q0, Q1, Q2, Q3. serial input. This is the output, parallel output. These are the output. This is MSB. This is LSB. These are the outputs. Output. Clear? Clear. So now, for suppose I want to give all 1, 1, 1. I need to be shift this 1, 1, 1. Serially, first what I need to do? First this one. Okay, CLK, SI. Okay. So after that, Q0, Q1, Q2, Q3. Okay, Q3. So now first clock pulse, 0 clock pulse, SI will be 0. So let's consider these all are 0. Let's consider these all are 0. Now clock pulse is 1. Now this SI will becomes 1. This SI will be stored in Q0. Yes or no? Q0. This becomes 1. This 0 will be shifted to here. This 0 will be shifted to here. This 0 will be shifted to here. Is there any output is getting? No. Next, what I need to do? Again, second clock pulse. Second clock pulse, what I need to do? So second clock pulse, one more one it will take. This is 1. This shifted to here. This will be shifted to here. This will be shifted to here. This will shifted to
0.
here. So third clock pulse, one more one. This will be shifted to here. This will be shifted to here. This will shifted to here.
0.
This one is 0. Fourth clock pulse,
1.
1. This one will shifted to here.
1.
This one will shifted to here. This one will shifted to here. This one will shifted to here. So now all the registers get a 1, 1, 1, 1. So now I can collect the data output, right? Directly from Q0, Q1, Q2, Q3. That is the 1, 1, 1. So how many clock pulses are required here?
4.
4 clock pulses are required. 4 bit you are passing, 4 clock pulses are required. So then 100 bits, how many clock pulses are required?
100.
100 clock pulses are required. So formula here is n bits, n clock pulses. Note down. N bits, n clock pulses. If I have a n bit, so then how many clock pulses are required? N clock pulses are required. N bit, n clock pulses. N bit, n clock pulses. Clear? Clear. So next two types we'll see in the next class. Then we'll start Millet and Murray missions. Clear? So any questions, any doubts today class? Online guys?
Can you 1, 1, 1 answer?
Which just I took the example. Anything you can take.
Okay. Example.
Example. This is example. Anything. See 0, 1, 0, 1 you can take. Okay. 1, 0, 0, 0 you can take. Anything. This is the data which I need to shift. That's it. Example this one is. Previous also I took some other example. 1, 0, 1, 0. This is example. Anything you can take. 4 bit, any number you can take. And you can shift.
0 to 4 bit.
This 4 bits, 4 bit, okay. So 1, 1, 0, 1, 0 you can take, or 1, 1, 1, 1 you can take, or 1, 0, 1, 1 you can take. Anything you can take. Clear?
180. 5 numbers.
Yeah. So machine will understand binary numbers only, right? That's why. So all are digital. In the digital, we'll only see 0 and 1. Okay. So that's the reason. I'm stopping here. Go with these things. So we'll discuss